All right, let's get started. Today's lesson is going to be on what is an annuity and how to calculate an annuity. And as I mentioned before, this might be one of the most important lessons in all of math when it comes to just regular life, because this is the way that you're going to actually be saving for your investment, for your retirement, in the future. What an annuity is when you're borrowing or investing money, usually investing money, and the initial amount doesn't remain fixed. So in the previous lessons on compound interest, we were talking about putting in a fixed amount of money, like depositing $1,000 in the bank and then walking away for 30 years, not touching that $1,000 and just letting it accumulate interest. But that's not usually the way that people will invest money. They'll usually invest money on a monthly basis. So they'll continuously change the amount of money in the bank with smaller regular payments. And that's what an annuity is. Each one of those regular payments gains interest over time. So here's an example. Allison is saving money from what she earns at her part-time job. She deposits $100 at the end of each month into a savings account that pays interest at 3% per annum compounded monthly. How much will she have saved up at the end of 1 year? So I'd like you to notice that some of the terminology is coming back from our previous lesson. 3% per annum, compounded monthly. So how much will she have saved up at the end of the year? Let's first calculate what our interest rate would be, which I've already done here. So 3% compounded monthly means divided by 12. 0.03 divided by 12 gives 0.0025. And we're going to use a table of values to go over how this works. All right. Now, I constantly mess this up, and I struggled with it yesterday a little bit as well. I think it's my problem with calendars. I don't know why I have issues with calendars. I know how many months there are in a year. But why does this first amount of money only get 11 months worth of interest? So you're depositing $100 at the end of the month. It is only getting 11 months worth of interest. Let's say that $100 was deposited at the end of January. That means the end of January, January's done. So that $100 doesn't have time to accumulate interest over that month. So it doesn't get interest in January, but it does get interest February, March, April, May, so the 11 months after that. And that's why you're only going to get 11 months of interest for that particular $100. So that $100, and notice that this is just the compound interest formula, principal times 1 plus I to the n. So we're using the compound interest formula for these annuities. And that $100 will gain $2.78 in those 11 months in interest. Now, if we go to the next month, that one's only going to have from March till the end of the year to gather interest. Therefore, it's going to gain less interest, 10 months worth. And on and on and on. The next one's only going to get 9. And you can see that the amounts of interest keep going down as time goes by, because you're depositing $100 in at the end of January, then $100 at the end of February, then $100 at the end of March, on and on and on. That means the last one that you're going to deposit is $100 at the end of December. That one doesn't gain interest. Okay, so it's just going to be that $100. These are all going to add up to give us our total of $1,216.64. So I'd like you to notice that had you put $100 in the bank every month, instead of putting it in the bank, had you put $100 under your mattress every month, not gaining interest, you would have ended up with $1,200 only. So there's $16.64 of interest, which I know is not a life-changing amount here, but this has only been 1 year. If you look at the way these numbers increase from the bottom of the table going upwards, this is a geometric series. We're multiplying by the 1 plus 0.0025, which is the R value in the geometric series, and that r value keeps going up in power. So it would be r to the 0, which would be 1 down here, r to the 1, which would be 1 plus I to the 1, and then r to the 2, which would be 1 plus I to the 2. So this is a geometric series. I want to therefore use the properties of a geometric series in order to show you the development of the formula for an annuity. So here's that proof. Now, starting from the bottom of the last column, like I just already explained, I want to talk about how did I generate this equation right here. So what is P? What is P times 1 plus I? I just want to be absolutely clear. P is the first amount of money that we introduced here in the bottom of the column. So it's the last amount invested. That's your P. And then this one would be P times 1 plus I. And then this one would be P times 1 plus I squared. And if we add all of those up, again, I want you to notice that the last power is 11, even though there are 12 entries, because we started at a power of 0, power of 1, power of 2, power of 3, all the way up to power of 11, and that's why this is an n minus 1. Now, in the previous example we did for 12 months, I used n, though, to represent any number of months. Before I move on, just a quick little thing here. There is another way to write a sum of a bunch of things that have a pattern like this. And I don't know how many of you have seen this notation before. The summation notation. Yes, the big E. Epsilon is the Greek letter. This is something that you're going to see probably next year to replace writing this whole long thing out here. Now, the way we would write it, we'd write P times 1 plus I to the n. And what we would say is that n goes from 0 to n minus 1. So you put the first index, and let me just put that here. This would be P times 1 plus I to the 0. All right, so that's the first index of our powers. And then this is 1 plus I to the 1, 1 plus I to the 2. So all you're doing is saying you're adding up all these terms, one after the other. They're all added. That's why it's called a summation symbol. From 0, where n is going to be equal to 0, all the way to n minus 1. So this is a nice little compact way of writing that entire thing. So if you see that symbol again next year, it won't hopefully be the first time you've seen it. So that was a little bit of an aside. So what are we going to do to this formula? Well, if you did this reading in the unit for sequence in the series, they followed the same idea to find the sum of a geometric series. I'm using 1 plus I instead of r, though. So as our second equation, what we're going to do is we're going to multiply every term on both sides of the equal signs by 1 plus I. Now that's going to have the following effect. If I multiply Sn by 1 plus I, it's clearly just going to be 1 plus I times Sn. If I multiply P to the 1 plus I to the 0, which is a 1, times 1 plus I, it just gives that. And every successive power is just going to get added to by 1, including the n minus 1. N minus 1 plus 1 will just be n. So we've basically shifted all of the powers over by 1 in this second equation. And then what we're going to do is subtract the two equations. If I subtract 2 by 1, I want you to notice that a bunch of things are going to cancel out. If I'm doing this minus this, that's gone. This minus this, that's gone. All the way up to P to the I plus P times 1 plus I to the n, which is going to be left over because the P 1 plus I to the n minus 1 is going to cancel out as well. What are the only two terms that are going to be left over? We're going to have a minus P. Remember, we're subtracting upwards here, so it's going to be a minus P, and we're going to have a plus P times 1 plus I to the n left over. And that gives this. We're then going to factor Sn from both of these terms, and we're going to factor P from both of these terms. that's going to give us this. So factoring Sn gives 1 plus I left over. Factoring Sn gives a 1 left over, and it's a subtraction. Same idea with the P on this side. I'm using square brackets here just to differentiate from the curled or curved brackets. Now what's interesting is look what happens inside this bracket. What is 1 plus I minus 1 going to give? These brackets can just disappear because they just have a coefficient of 1. That just leaves us with I. And if we want to isolate for Sn, our final sum, we end up with this formula here. Now, in finance, we don't like to use this formula in this format. There's a couple of substitutions of variables we're going to do. First one is we're going to not talk about principles anymore because that could throw somebody off if they don't understand what's happening. We're going to use R instead of P to represent the regular payment that's being done over time. And we're going to replace Sn by A, which is our final amount, which we've always used for the final amount. It could be also called the future value. So this is the formula that we're going to be using. And this right here, folks, like I said, for the math student as well as the average person out there in the real world, this is one of the most important equations of your entire life, because that equation is going to control how you're going to save money for your retirement. And this is what all of the different variables represent. I is the interest rate per compounding period, like it was in compound interest, and N is the same thing as for compound interest as well. So those two quantities don't change. Obviously, the format of the formula has changed, and there's the R that's the new variable here. I forgot to turn on the mic, didn't I? Thanks, chat. I did the exact same thing in the previous lesson. Where did I lose you, folks? What was the last thing you heard? Did I explain how important that formula was to everybody? Did I say that part at least? Okay. So it was just when I basically called up the calculator. I'm not sure why calling up the calculator made my mic mute, but oh well. Okay, so we'll start from there then. Thank you for letting me know, chat. Where was I? Oh yes, so we're just typing in this formula, and as long as you follow BEDMAS properly, you'll be good. And as I was saying while I was muted, there is a double bracket here. On this calculator, it actually tells you that it's the second bracket. Some calculators don't tell you that, but they will show it to you in the window, right? So we're going to do 100 times bracket bracket, 1 plus 0.0025, close the first bracket, power of 12, minus 1, close the second bracket, divided by 0.0025, and all in one step I get the exact same answer, 1216.64. And if we go back to the table, that was the value that I got, sorry about that, at the bottom of the table right here, 1216.64. So it's the exact same thing, all done with that one formula now, We no longer have to worry about doing tables of values. We can just use that formula from now on. Whoa. I'm not sure what's happening with my tech here. Okay. I'm going to do one thing that might fix my issues. I was trying to show two things at once on my screen, and maybe that was causing the problems. All right, hopefully that'll reduce the issue here. So let's take a look at an actual problem. So given an ordinary simple annuity with semi-annual deposits of $1,000, earning 6% interest per year compounded semi-annually over a 20-year term, which of the following results in the greatest return? So what we're going to look at is a bunch of different scenarios that are going to change the amount of money we're making, and we're going to try to figure out what's the best one. The first one is going to be doubling the payments, but before I can do that calculation, I actually have to calculate what the regular amount of money we would get from this investment would be. And I didn't leave enough room to do that, so I'm going to try to fit it in right here. All right. So what tells us that this is a annuity problem and not a regular compound interest problem? It's right here. It says semi-annual deposits of $1,000, and that's the kind of wording that you might see. They might say regular deposits. They might say deposits of $1,000 every month. So that's the new type of terminology you're looking at in these questions to differentiate them from a regular compound interest question. So that's going to be our R value. Now, as always, we should calculate I and N before we do anything else. I is 6% compounded semi-annually. Quickly, chat, which one is semi-annually? That's right, it's twice per year. So we're dividing that by 2, which gives us 0.03 overall. Now our N value is based on how much time has elapsed for this investment. We're going 20 years twice per year. That's 20 times 2, which means 40 payments of interest. So we're going to put that in the A formula. Now this is part B here. Don't worry about that. I just need a little bit more room. So my A is going to be my regular payment of 1,000, bracket, 1 plus I, 0.03, to the power of N, which is 40, minus 1, close the bracket, divided by I. And I'm just going to use curly brackets. You don't have to use the square brackets if you don't want to. And off screen, I'm going to use my calculator. Hopefully I don't mute anything again this time, just to calculate that. So 1,000 times bracket, 1 plus 0.03, close the bracket, power of 40, minus 1, close the second bracket, divided by 0.03. And that's giving me $75,401.26. So that's how much money with interest you would have made by investing it for 20 years. Now, what's going to happen when I double the payments? Well, here's the nice thing about this scenario. I do not have to do the entire calculation over again, if you understand one little concept here. The only thing that's different between the equation that we just did and this one is the fact that the 1,000 became 2,000. Well, if I write that 2 times 1,000, which is what 2,000 is, now the only difference is there's a 2 times multiplying that entire equation. It's the exact same equation, except 1,000 has been multiplied by 2. That means my final answer is just doubled, which I believe is $150,802.52. So it's just a doubling. When you double the payment, which is changing the 1,000 to 2,000, you're just doubling the final amount. So that part of the equation or change is actually kind of a linear change. But doubling the interest rate is not. If we double the interest rate, 6% is becoming 12%. That means 0.03 is becoming 0.06. Nothing else changes. So let's plug in 0.06 into our equation. and calculate our new final amount. So the I in both of these positions change. And again, I'm just going to do this off screen. I'd love to do it on screen. Here, I'm going to try and I'm going to check, make sure my volume doesn't turn off again. Okay, so hopefully everything's still good. So I'm just going to clear this out. 1,000 times bracket 1 plus 0.06 bracket power of 40 minus 1 bracket divided by 0.06. And that's giving 154,761.96. $97 if I round it off. So that's a pretty significant difference. I mean, look at how much money you would have gotten at 3% per half year, so 6% overall. This is what you're getting at double the interest rate. So 12% divided by 2 for 6% every half year, which is greater than just doubling the payment. So far, doubling the interest rate is by far the best deal. What if I double the frequency of the payments and the compounding? So what does that mean? What was the frequency of the payments and the compounding frequency? The compounding frequency was semi-annually. What does semi-annually become if I double it? Semi-annually is, I think there's only one L there. Could be wrong. That looks weird. Whatever. What's the double of semi-annual? Thank you for the spelling. What's the double for that? No. If you're doubling the frequency, careful, and I was worried that some of you might make this mistake. What I mean is you're doing twice as many payments per year. So you're going from semi-annually, and that's right, chat, you're going to quarterly. You're going to 4 times per year. You're doubling 2 times per year to 4 times per year. All right. If you went to annually, that would be once per year. That's half as many times. We want to double it. Okay. There's an R there. So quarterly is what we want to do. And that's going to change both I and N. I is going to become, now we're going back to our original interest rate, which was 6%. So we're going to do 6% divided by 4, which I believe is 0.015. It's half of 3%, right? And then our N value is going to be 20 years times 4, which is 80. So before I complete this, do a little prediction in your mind here. Do you think this quantity is going to be greater than doubling the interest rate? Smaller than doubling the interest rate? Is it going to be greater than doubling the payment? What do you think is going to be happening with this one? Just think about it. You don't have to write it. If you want to put it down in chat, see if you're right or wrong. It's just a prediction. So $1,000, 1 plus I to the N, so 0.015 to the power of N, which is now 80, minus 1, all divided by 0.015. More frequent does mean more money, but does more frequent with less interest rate mean more money? So 1,000 times bracket 1 plus 0.015 bracket to the power of 80 minus 1 bracket divided by 0.015 equals 152,710.85. It is less than doubling the interest rate. It is more than doubling the payment, and it is definitely more than just doing it at the smaller interest rate. Okay, but the comparison between this example and this example that I'd like you to see is that even though you had less payments, 40 versus 80, your interest rate was 0.06 compared to 0.015. And that makes the difference significant. So people that invest money are always searching for the best interest rate they can possibly get. That's what stock market analysts are always doing. What is the best interest rate you can possibly get? Banks, same thing. All right, we're going to finish off with this one last example. What most people want to know is, what would I have to invest right now, starting today, monthly, to end up with $1 million for my retirement? And in a case like this, I'm telling you the final amount. We don't know our regular payment. Can we take this formula and rewrite it to get R by itself? And the answer is obviously yes. And even though this looks quite daunting, it really isn't. Because this whole bracket is just multiplying R, and I is just dividing R. If I want to isolate R, all that happens is the I comes over here and multiplies, and the big square bracket goes underneath and divides. And now we've got R isolated. So let's put all of these numbers in. Now we're going to have to calculate our I and our N separately here. If you hear that buzzing in the background, folks, it's just my dryer telling me my clothes are dry. So we've got 7% interest per year compounded monthly. So we've got to do 7% divided by 12. I'm just going to do that off to the side here. So 7%, which is 0.07, divided by 12, gives 0.00583. We're going, now if we're starting at age 20, now be very careful with these kinds of questions, folks. It is very easy to want to say that 20 years have gone by, but we're comparing it to 65. So how many years have gone by from from 20 to 65? That's 45 years, right? So we're doing 45 years times 12. And that gives 540. 540 payments of interest over a 45-year period. So let's put all of our values into the formula. Our A is $1 million. I want to know, how much money do I have to put in monthly starting at age 20 at an interest rate of 7% to end up with $1 million? Okay, let's bring my calculator back on the screen here. Show you to calculate that. So I'm just going to delete everything else, start from fresh screen. So $1 million, that's 6 zeros, times. Wait a second, I just messed up. Oh, darn it. I wrote everything upside down, didn't I? Sorry about that, folks. Let's see if I can... I'm going to try something here. See if I can make this easier on myself. I was too excited to show you the final answer, and I messed up putting it into the formula. Magic of smartboards, I can fix this. Sorry about that. So A times I divided by the big bracket there. And now I got rid of my calculator. Let me bring it back. Sound's still on. Okay, we're still good. All right. So let's try this again. 1 million times 0.00583 divided by our big bracket. Bracket. 1 plus 0.00583 bracket, power of 540 minus 1, bracket again, equals $264, basically rounded off to $264. So I want you to think about that, folks. If you put $264, if you found a way to do that, into the bank every month in an investment that gave you 7% interest, which is what's going to be hard to find. It is possible to find 7% interest average investments in a mutual fund and stuff like that, but right now investments are a little bit rough. So anyway, but if you could do that, from age 20 to age 65, you would have saved $1 million in the bank. And that number is not completely unattainable. And if you started even younger, at 18, you'd have a couple extra years. It would be even less than 264. If you start even younger, it'd be better, but you can't open an investment account until you're 18, unless somebody else does it for you. So, what would be the problem, or how much would it change if we started at 35 years old instead? What about if we started at 50 years old? Yeah, it would be, and it could potentially be significantly more money. And that's your homework for tonight. That's the only thing I'm giving in homework, is to figure out what would be the difference in the R value if you were starting at 35 years old, which means you have 15 years less, or if you started at 50 years old, which means you'd have 30 years less to invest. Yeah, you'd have to, or you could find a significantly higher interest rate, correct. But at the same interest rate, I'd just like you to see what the difference is. Okay? So that's the end of the lesson. I'm going to stop recording at this point. I'll stay on stream for just a couple more minutes.